math than physics, really, but it's going to deal with how to propagate uncertainty through a formula with a function that deals with two or more variables. So as an example, I'm going to take a calculation of the gravitational force between two objects. So we have this formula for the gravitational force between two objects. It is equal to the universal gravitational constant g multiplied by the product of the masses of the two objects divided by the square of the distance between them. And let's suppose we have nominal values for the two masses and the distance with some uncertainties given to the right. And let's assume that the value of g is exact. It has no uncertainty. We want to know what is the uncertainty in the force value. So when you have a function of two or more variables, if those variables are all independent of one another, the way the uncertainties combine is not via simple addition, but they add in what we call quadrature. So for example, if I just have some simple function like f of xy is just equal to the sum of x and y, if x and y are both independent and they each have an uncertainty, the uncertainty in the value of f, which I could call delta f, is not simply the sum of the uncertainties in x and y, but it is given by this expression here. And a good way to understand why this would be is assume you know the position of some object to within plus or minus 1 meter in the east-west direction, and also plus or minus 1 meter in the north-south direction. So the greatest possible uncertainty you would have in the position for that object is if you were off by 1 meter to the east and 1 meter to the north, which would put you not 2 meters away, but the square root of 2 meters away from the true position of that object. So in general, the way that you would express the uncertainty if we have just some unknown function of x and y, the way you would calculate the uncertainty in f is with a formula that sort of looks like this. So we want the uncertainty in f that results from the uncertainties in x and y. So the uncertainty due to the uncertainty in x would be given by this expression here. And then for y, we would have something similar. So what these expressions mean really is this is, first of all, it stands for the partial derivative of f with respect to x. So it's basically you're taking a derivative of f with respect to x, assuming that all other variables are held fixed. So this quantity here tells you how much f will change for a given change in just the variable x. And if you multiply that by the amount of change in the variable x, then that product gives you the resulting change in f that comes as a result of the uncertainty in x. And then similarly, this quantity here would give you the uncertainty resulting as a function of the uncertainty in y. All right, so this is sort of the general formula that we want to apply to our gravitational force expression, which is actually a function of three variables, m1, m2, and r. So the uncertainty in our force is going to look something like this. So we'll have the square root of, we'll have three terms inside here. We will have the derivative of f with respect to m1 multiplied by the uncertainty in m1, and then we'll have the derivative of f with respect to m2 times the uncertainty in m2, square that, and then take the derivative of f with respect to r and multiply that by the uncertainty in r. Okay, so now we just have to work out what each of these three derivatives is equal to. All right, so our first derivative with respect to m1 is just in the numerator, it's to the first power. So this will be g times m2 over r squared, and then multiplied by delta m1. If we take the derivative with respect to m2, we get g times m1 over r squared times delta m2. And then when we take the derivative with respect to r, we have r to the negative second power. So when we use the same differentiation rule, we multiply by -2, and then decrease the power of r by 1. We get minus 2g m1 m2 divided by r cubed, and then multiply that by delta r. By the way, just something I would point out here, each one of these terms has to have the correct units for force. So delta m1 has the same units as mass. So we still have g multiplied by 2 masses divided by r squared, same thing here. Here we have g multiplied by 2 masses divided by r cubed, but then we have this uncertainty in r, which has the same units as r. So effectively we have 2 powers of length in the denominator, so this still has the same units as well. So this is all good, has the right units, and if we plug in all of the numbers and actually do the calculation, we end up getting that the force is equal to about 1.79 times 10 to the negative 13, plus or minus 1.07 times 10 to the negative 13 newtons.